If you trip and fall while walking down the street right now, you are going to hit the concrete and you are going to scrape your knee.
Oh, absolutely. And it's going to hurt. Viscerally.
Exactly. But what if I told you that the concrete you just hit isn't actually made of matter?
Right. It sounds absurd.
It really does. What if the pain radiating up your leg is just, the physical sensation of a universal algorithm rejecting a math error?
That is the exact paradigm shift we are looking at.
Welcome to the deep dive. Today, we are taking a massive, incredibly dense stack of theoretical physics, cognitive science, and computational philosophy, and we're distilling it down.
We are going to try our best anyway.
Yeah, exactly. Our mission for you today is to fundamentally rethink the universe. We're going to abandon the comforting idea of static physical stuff, the concrete, the trees, the stars, even your own hands.
We have to completely let go of that Newtonian worldview.
Oh, right. Instead, we are replacing it with a mind-bending framework called informational ledger theory, or as it's sometimes referred to in our sources, emergent ledger theory.
It is a really profound shift in how we perceive reality. I mean, we are so used to the idea that the universe is a giant empty box.
Like a stage.
Right, a stage. And inside that box are billiard balls. Planets, atoms, people just bumping into each other according to predictable mechanical rules.
But when you look at the research we're unpacking today, that entire mechanical worldview it completely falls apart.
It shatters. And we aren't just going to sit here and list scientific terms for you today. We're going to connect the dots.
We have to, otherwise it's just jargon.
Exactly. We're going to explain why viewing the universe as a dynamic, self-organizing computational system solves some of the most frustrating, lingering mysteries in quantum mechanics and cosmology.
Okay, let's unpack this, because by the end of our time together today, you're going to have a shortcut to understanding the absolute cutting-edge intersection of quantum mechanics and consciousness.
You'll have a completely new lens to look through.
Right, you'll be armed with a framework that changes how you view the world around you and, honestly, how you view your own mind. But to get there, we have to start at the absolute bottom.
The very foundation.
Yeah. If the universe isn't made of physical stuff, what is the base layer? Like, if we are talking about reality as a computer, we need to know what the hardware is made of before things like atoms and planets even exist.
Well, to understand the hardware, the sources introduce a concept inspired by the computational theorist Stephen Wolfram. It's known as the Reuliad.
The Reuliad, okay.
Yes. The Reuliad is described as an unbounded configuration space. It basically exists as a superposition of all possible computational rules and states.
I want to slow down right there because unbounded configuration space and superposition is exactly the kind of dense jargon we need to translate for this to make sense.
Fair enough. It is quite a mouthful.
Let's start with superposition, since that's a term thrown around a lot in quantum mechanics. Usually when people hear superposition, they think of, like, Schrödinger's cat.
The famous thought experiment, right?
Yeah, the idea that a quantum particle exists in multiple possible states at the exact same time until someone observes it. And at that point, it just kind of picks a state.
That is the standard quantum mechanical definition, yes. The particle is essentially a probability wave.
Right.
But the Reuliad takes that idea and scales it up to absolute infinity. We are not just talking about the physical position of a single electron being in superposition here.
So we're going way bigger.
Much bigger. The Reuliad is a conceptual space where the fundamental rules of mathematics and logic are in superposition.
Wait, the rules themselves?
Yes. Think of it as a library containing every single possible rule for how information could ever interact.
Oh, wow.
It contains the rules of our physics, sure, but it also contains rules that generate pure, chaotic gibberish, all happening simultaneously as pure potentiality.
So if I'm picturing this, it's not like a physical void filled with floating numbers. It's more like a churning ocean of raw logic.
That is a very good way to visualize it. An ocean of infinite logical potential.
But how do we get from a churning ocean of every possible rule to something specific? Like, if everything is possible everywhere all at once, nothing can actually happen, right?
And this is where we see the first mechanism of reality emerge. The sources call it nucleation.
Nucleation, like in chemistry.
Exactly like in chemistry.
Right.
In chemistry, nucleation is how a crystal forms in a solution. A few molecules just happen to align perfectly, and they create a tiny seed that the rest of the crystal grows around.
Okay, so how does that work in a sea of math?
Well, in the Reuliad, we get computational nucleation. Because this space of potential is truly infinite, statistically, certain rule sets will briefly align and interact just by pure chance.
Just random statistical luck.
Right. And the sources refer to these spontaneous, localized formations of rules as chiplets.
Chiplets. Obviously not little pieces of silicon from a tech factory.
No, definitely not physical chips.
We're talking about microscopic temporary bubbles of code. Our sources compare them to cellular automata or quantum vacuum bubbles. And I actually want to bring up cellular automata for a second to ground this.
I think that's a great idea. It perfectly illustrates the point.
Yeah, because it's crucial for understanding how simple rules create complex reality. The most famous example is John Conway's Game of Life.
A classic computer science demonstration.
Right, and it's just a grid of squares on a computer screen.
Yeah.
The rules are incredibly simple. If a square has too many neighbors, it dies and turns black.
Overpopulation, essentially.
Exactly. And if it has the right amount of neighbors, it lives and turns white. That is literally it. Those are the only rules.
But the results are staggering.
They are. From those tiny, rigid rules, if you let the program run, you get massive, complex moving patterns. They look like little spaceships and pulsing organisms flying across the screen.
That is a highly relevant parallel to draw here. Conway's Game of Life demonstrates that you do not need a complex, overarching blueprint to build a complex system.
You just need the rules.
You just need a basic rule set and the ability for that rule set to iterate over and over again. A chiplet in the Ruliad is essentially a spontaneously nucleated cellular automaton.
A tiny bubble of rules.
Yes. It is a tiny, localized rule set that pops into existence and defines how information behaves in that microscopic conceptual space.
Yeah.
So reality begins as this bubbling froth of raw, competing chiplets.
So hold on, I see a major mechanical problem here. Let's stick with the computer analogy.
Okay, what's the problem?
If I boot up a massive open-world video game, the computer has to render the graphics. It has to calculate where the light bounces off a puddle, how the wind moves the leaves on a tree.
It takes a lot of processing power.
Right. If the computer tries to calculate every single leaf and the reflection of every leaf down to infinity, the processor just maxes out. The game crashes, it freezes.
It hits a wall, mathematically speaking.
Yeah. And in computer science, this is related to Alan Turing's famous halting problem. If the universe is a computer, and it has this infinite Ruliad bubbling with infinite chiplets running infinite rule sets, why doesn't the whole system just freeze up?
It's a fantastic question.
Like, how does the universe avoid the halting problem?
You have hit on the exact hurdle a purely algorithmic, Turing-based universe would face. Alan Turing proved mathematically back in 1936 that there is no general algorithm that can determine whether every possible computer program will eventually finish running and halt, or if it will run forever in an infinite loop.
It's just impossible to know in advance.
Correct. If the universe were just a standard Turing machine trying to calculate every consequence of the Ruliad to infinity, it would indeed hit the halting problem. It would get stuck in infinite recursive loops.
So it would just crash.
Exactly. To prevent this, informational ledger theory suggests the universe utilizes what the sources call non-algorithmic Gödelian leaps.
Gödelian leaps. Taking us from Alan Turing to Kurt Gödel, the mathematician who basically broke mathematics.
He certainly shook its foundations.
Yeah, Gödel's incompleteness theorems prove that in any logical system, there are true statements that simply cannot be proven using the rules of that system.
You can't calculate your way to every truth.
Right. Sometimes the system has to just jump outside of its own logic.
Precisely. A Gödelian leap means the universe has a built-in mechanism to resolve paradoxes and force a state collapse without having to linearly compute every single infinite microscopic step.
It just cuts to the chase.
It does. It doesn't calculate to infinity. It makes a non-algorithmic leap to a conclusion. And the physical mechanism it uses to enforce this leap, to keep the cosmic computer from freezing, is the Planck constant.
The Planck constant. Max Planck, the grandfather of quantum theory.
The very same.
We usually hear about the Planck length, or Planck time, as like the smallest possible measurements in physics. You literally cannot divide space or time into smaller chunks than a Planck unit.
Yes, and in the context of informational ledger theory, the Planck constant acts as the universe's absolute clock speed. It is the fundamental frame-rate limiter.
Oh, I see.
By enforcing a strict minimum size and a minimum tick of time, the Planck constant forces this bubbling quantum potential, these chiplets, to stop calculating their infinite possibilities and actually render into a definitive state.
So it literally is a video game frame rate limiter.
It functions exactly like one.
A video game doesn't calculate the physics of a rock if you aren't looking at it, and it caps the update speed at, say, 60 frames per second. If it tried to do 1,000,000 frames a second, it would crash.
Right, the hardware couldn't handle it.
So the Planck constant is the universe's internal clock saying, okay, time is up, stop calculating.